Welcome back to another video of my journey through interview prep. Last video we worked on the problem that has to do with adding two negabinary numbers, and I spent over 2 hours trying to explain the logic behind it and understand the process of addition that happens. And we crafted a solution that we're going to go over right now. So the goal for this video is to explain the solution one more time and to optimize it. So we're going to understand again how negabinary numbers work. We're going to perform one example. For the extensive video and research, you should watch my previous video. I will have the link in the description. And the second thing we're going to do for this video is we're going to optimize the previous solution that we came up with. So last video we just came up with a solution that works, but for this video we're going to optimize it more, and we're going to focus on what items of the performance we're going to optimize, like space and complexity. And we'll walk through the code and I'll explain what happened, what we will do for optimization. My answer is not perfect. There could be other answers out there that I haven't thought of, but I'm just considering myself as being interviewed by an engineer, and I'm just explaining my thought process, so that will be helpful to everybody. All right, so let's start looking at, let's first start with explaining the concept of negabinary numbers and how we add it. So I'm going to move to my notebook. So a negabinary number is a binary number with a base -2. So if we have a number that is 111 and it's in base -2, the way we will come up with what this number is similar to the way calculating the decimal value of a binary number works, except that we replace the base. So here we're going to do -2 to the power of 2 plus -2 to the power of 1 plus -2 to the power of 0. And doing some quick math, this will come out to 4 minus 2 plus 1, and that will give us 3. So this number right here is 3 when the base is -2. But what if the base for this number compared to binary, let's calculate what this number is equal in binary. So that will come out to 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0, and that will give us 4 plus 2 plus 1, that will equal to 7. So we can see how these numbers are different because of the different pace. So this is the negabinary numbers that work on a negative base. So let's take a look at our problem, and we'll come back to the notebook one more time. So the problem goes over, or the problem is figuring out how to add two negabinary numbers. The first number that will come into the input function is an array of zeros and ones representing the first number, and the second number is another array 1, array 2, representing the second number. They're both in base -2, and what I need to figure out is add them together and return the result. So return the result of adding array 1 and array 2 in the same format that they came in. If you want to watch the full detailed walkthrough for the solution, make sure you watch my previous video. But for that, and through the previous video, that's the answer that I came up with. But for the purpose of this video, I'm just going to show a quick example of how do we add two negabinary numbers, and we're going to start optimizing this solution. So I'm going to go back to my notebook, and we're going to start by adding two negabinary numbers. So here we're working in the following base. And I'm going to do the same work in decimal for demonstration purposes. So let's say I take the number 1101. I don't know what is it, but I can calculate it here. So that's negative 2 to the power of 3 plus negative 2 to the power of 2 plus negative 2 to the power of 0. And notice here we skipped the power of 1 because the power of the index of 1 here is 0. So this will give us the number negative 8 plus 4 plus 1. That will give us negative 3. So this is negative 3 right here. So this number is negative 3. And I'm going to add it with another random number. Let's take the 3 that we came up with. So let's try to add it with 1, 1, 1. And let's see how that works. So in binary, we just add 1, 1. And in Negabinary, we're going to do the same. So 1 plus 1 is 2. So I'm going to try to, okay, so 1 plus 1 is 2. What we used to do in binary is take the 2 and in decimal and see how is it written in binary. So in binary, 2 is written as 1, 0. And what we used to do is we used to drop the 0 to the answer and carry the 1 to the next answer. But in Negabinary, we have the number 2, but this won't give us 1, 0, just like binary. 2 in Negabinary is 1, 1, 0. And to prove that, I'm going to say negative 2 to the 2 plus negative 2 to the 1 plus, and that's it. So I'm going to get 4 minus 2, and that will give us 2. So this is the number in Negabinary, and this is the number that I need to use. So we'll do something similar to binary number addition, is we'll drop the 0 to the answer. That means I'm going to write a 0 here, and the leftover is 1, 1. But what is 1, 1 in base 2? In base negative 2. So 1, 1 in base negative 2 is negative 2, 1, and plus negative 2 to the power of 0. And that will give us negative 2 plus 1, and that will give us negative 1. That means the carry that we're going to have to the next pair to the left will be a negative 1. And let me put it in red. So we got a negative 1. We got a negative 1 because the leftover right here was 1, 1, and 1, 1 in Negabinary is negative 1. So now I have the first result. Now I'm going to look at the second pair right here. For this one, we're going to have negative 1 plus 0 is negative 1, plus 1 is 0, so I get another 0 right here. Then the same process happens for this pair. I have 1, 1, and 1, 1 is 2. 2 in Negabinary is 1, 1, 0, so I'm going to put a 0. And what's left, which is the 1, 1, means negative 1 in Negabinary, so I'm going to have another negative 1 right here. Then negative 1 plus 1 is 0. So we're going to get 0 right here. So we got 0 for this number. And does this make sense? It makes sense because we added the positive 3 to negative 3. So I got a 0. So that would be the example, a quick example of how adding in Negabinary numbers work. For a more extensive example, check out the previous video, but I'm going to move on. So with this example in mind, we crafted this solution from last video. So let's spend some time optimizing this solution a little more and looking at some fine details of the solution that we can make a little better. So the first thing, or there's a couple aspects that we can look at. So we can look at the logic, and improving the logic will improve the complexity, it will improve the performance of the solution. And we can look at the storage using, or storage usage. That means how many variables are we using? Is there too much? Are we copying too much to a new variable for no reason? And focusing on the storage will optimize the storage. Focusing on the variables and the way we use the storage will optimize the storage performance. And so we'll start first with the storage. Let's get storage first. So in this solution, we end up making an answer array. And the answer array stores the answers that we get from adding each position in the argument arrays. And we take this array and we return it in the end after getting rid of the leading zeros. So now the question is, if we're only looking at storage right now, how can we improve, or what's the current performance for storage, and what could be improved to? So the current performance of storage is big O of n, because this array will grow based on how big array 1 and array 2 is. There is a special case where if array 2 and array 1 represent the same number, but one of them is negative, like -3 or 3, that means our answer array will just be an array of one element, which is 0. But in other cases, or in general, the answer array will grow to be as big as array 1 or array 2. So we have a big O of n type of solution as far as storage for this solution. So how can we improve big O of n? It's either we can do fine-tuning on the answer and still end up with a big O of n solution, or we can think of how can we make the solution with constant storage. Now, for constant storage, that means we can't have any type of variables that depend on the input. So here, we can't have any variables with size that depends on the input. So here, the carry variable, it has the same size, it won't change, it's just an integer. The answer is an array, it will grow with the answer. Biggest size variable, it will be the same size. And array reversals, that's nothing new. And these variables will stay the same, they won't grow. So the only variable that is growing with this with the arguments, or the only variable related to the size of the arguments is this answer. So maybe we can make it better by getting rid of it. If we got rid of the answer variable, we will be able to have a constant space solution. That will be big O of 1. So let's think about how can we do it. Well, a quick thinking, or the straightforward solution is like, hey, let's just get rid of it. But if we got rid of the answer array, where are we going to store the answer? Well, a possible solution could be like, hey, let's use one of those incoming arrays. Let's use one of those incoming arrays to save the answer, and we return this array right here. This way we'll get rid of the answer array. So let's see how can we go about that solution. So I'm just gonna wipe away my answer variable. I'm going to choose array 1 to return, and it doesn't matter that much. But maybe we can choose the bigger array to return our answer. But actually, it does not matter that much because you are checking. With the way the logic's set up right now, the array that we use does not matter that much. So we're going to start with using array 1 as the array to hold the answer. So as we notice here, we use the answer array to add a specific answer, but what we can do instead is change or add this result or add this answer. So this 0 right here, this one right here, they're going to be part of the answer. So that's why we do answer unshift. And the unshift here means that we're appending it to the head or to the beginning of the answer array. But now we don't have an answer array. We want to add it to the array 1. But one complication here is that we want to make sure that we're not overriding data that we're going to look at in the future. We can override data that we finished processing. So as far as array 1, I can see that I read the data from array 1 from this line 15, and I store it in A. So if I overrode this position, it won't be a big deal because I already knew what the value is and I used it to calculate the result. So I'm going to go ahead and instead of unshifting and adding to the head of the answer, I'm going to use array 1 at index I, and that's going to equal to the answer that we want. And I'm going to do the same for each one of these array shifts. And again, this will not be a problem because we're overriding data that was already consumed. So I don't care for the data I'm overriding here. Right here and right here. All right, so now I'm adding the answer to the argument array while I'm calculating the result of adding two numbers. So, okay, I have that set up, but also I noticed that I used the answer variable here, so let's see how that can change. So here I'm trying to add new variables to the answer. And that depends whether I have a carry left or I don't. So the way we're going to handle this is by adding the data to array 1 again. So the variable I, it's not only declared for the for loop, it's actually declared for the function block. As far as I know, with the let keyword, it's block. What is the term? The let keyword in JavaScript. Let's research it real quick. Block scope, that's the word that I'm looking for. So I is block scoped. That means I will be available in this function. So I can use I even outside the for loop. So, and I know I is at the last position of the pair, and I can use it to add the extra stuff I want. So I can do array 1 I that equal to this. Or actually, I can just use and shift to do it, to be a little safer. Maybe using the I variable outside the for block might not be a good practice. So I'm just going to do array1 on shift, and oops. And I'm going to use array1 on shift. So here I add my answers to array1. Then the last step in my code was getting rid of the leading zeros. So here I'm checking the first element of my answer, and I'm getting rid of the zeros. So my answer right here is array1. It's not answer anymore. And my answer, the same thing right here, array1. Just copy it. And I will just return array1. Let's see if it works on one of the samples, and it doesn't work. It gave me 1, and it overrode all these zeros in the beginning. So let's see what is happening. Okay, the problem here has to do with reversing. That means because I'm adding the answer in a reversed way, starting from 0 all the way to the end of the array, and that will cause the leading zeros logic to run and get rid of the 4 zeros in the beginning. So for now, to mitigate this problem, I'm just going to reverse back the array. Actually, I'm going to reverse it right here, because the handling the carry logic will add to the beginning, but that assumes that the beginning is the most significant. But the way the array exits the loop, the beginning is the least significant. So I'm going to reverse it, array1 dot reverse. Let's try it right now. All right, reverse, E. All right, so now it works. Let's submit the solution. And it looks like a pretty quick solution, 60 seconds. But again, as I said in last videos, I don't really trust these numbers. It's nice to be in the faster than 100%, but I don't trust these numbers. But you can notice that maybe the memory usage has decreased a little bit. So hooray, now we have a solution with constant space. I'm using one of the arguments for this function as a way to pass it as an answer. Okay, now we optimize solution. Now we can tell the interviewers, like, hey, I have constant space for this solution. It's optimized. Now the next thing we're going to optimize for is the logic. Like, how can we make the logic cleaner, get rid of unnecessary operations, and increase the performance. So the performance of this function, it is big O of n, given that n is the size of the array of the input. Because here we loop through each array element of the inputs, and we process. We do some processing on them, then we do some XOR logic right here. Can we improve the solution to be constant speed? I doubt it, because we have to look through each element of the input arrays to calculate our answer. But what we can do is make the logic cleaner and a little more understandable by getting rid of the extra operations. All right, so let's see. I noticed that parts of my code uses strings for the arrays, and that should be wrong. The arrays are all in integers, so I'm going to quickly get rid of all the strings that I've used. And the reason this is not a problem here is because JavaScript is a little lenient when it comes to this stuff. If you're trying to compare an integer to a string, it'll try to parse the string as an integer and see if it's actually an integer. So most of our strings were actually integers inside of it, so it was able to work just fine. And because I'm not dealing with strings anymore, I can get rid of the parse ints right here. Okay, let's give it another test, and it still works. So the strings is not a problem. So let's look at some of the reversal logic. So the way we reversed the arrays right here is we can get rid of the padding step. And the padding step, we had a piece of logic that will look at both arrays. It will take the smaller array and it will make it as big as the big array, so we can loop through the elements. So if we got rid of that logic of padding and I reversed the arrays, that means I'm going to have to check when I ask for an element from an array, does it exist or not? Because I know my arrays are different sizes, and if the element does not exist, I'm going to return a 0. And because we're reversed, we have to walk through the arrays from the beginning, because I know as the input, the most significant bit the arrays are ordered from most significant to least significant. So this one right here on the left at index 0 is the most significant. So this one is the one that will have a power of 4. And this 0 all the way to the right is going to have the power of 0. So when we reverse them, and before we reverse, if the array was in this shape and I want to do my addition, I have to look at the least significant bit first, so I need to start my addition from the last element, just like we did in the notebook. But if we reverse them, if the most significant was on the left and the least significant is on the right, I need to traverse the array from the back. But since I reverse them, I can traverse it from the beginning, and I have I set to 0. But reverse operations on big arrays might be expensive, so we could just get rid of the reverse logic and walk through the arrays from the back to the front. But again, if we got rid of the reverse logic, that means we have to pad. So let's pad, and let's walk through the logic, through the arrays from the back. So my index is going to be set for the last index, which is the biggest -1, and my I should be bigger or equal to 0. I'm going to go all the way to the beginning of the arrays, and I'm going to decrement I. I'll get rid of my reverse logic, and I will pad. So I'm going to add padding of zeros to smaller array. So now I need to know which one is the smaller array so I can pad it to be as big as the big array. So to calculate the small array, I know the biggest size. I know here we're trying to calculate the maximum of those two lengths, those two arrays, and I can walk through it. But that does not matter that much, because if I padded the array, they will be both the same size, and it doesn't matter which length I ask for. So I'm going to get rid of my biggest size right here. And I'm just going to make variables that will tell me which one is the small array. And that should do it. Then I'm going to have an if statement logic that will tell me what's the small array. Actually, I might be able to do it through a ternary expression. So I have like array1 dot length bigger than array2 dot length. That will give us array2 is the smallest, or it's array1. So this should be easy to read. If array1 has the bigger length, that means array2 is the smaller, and if this is false, that means array1 is the smallest array. So now we gotta pad the array with a number of zeros. The way we can pad it is, if I know the smaller one, I can compare it to the big one and see the difference in size and pad it all the way till the sizes are equal. So I can do while array1 dot length does not equal array2 dot length. I'm going to take the smaller array, and now I'm going to pad it in the beginning using the unshift function with a 0. And I keep padding until both sizes are the same, and that's how I know that, well, that's how I know how both sizes are the same. So now I can just ask for any of the array lengths, because they're both the same, and I can run through my logic. Now I don't need to ask whether this item is undefined or not, because I did padding, and I know that these elements are going to exist. Now I need to check if an element is undefined. Both arrays are the same size. Let's do a quick run. Wrong answer. Okay, it's because I'm still reversing right here. Another run. All right, it works. So now we cleaned up the reversal code, and we just added a smaller piece of code to find to pad. Can we do a little better? Let's see. Let's walk through the code. Okay, let's look at some of our calculating the results. So here I check if the result is 2, if it's 3, if it's -1, else do this. One thing we can notice with those two statements is that the result is bigger than 1. And also, one thing to mention, since we're dealing with negabinary numbers, the numbers that we expect to deal with are just zeros and ones. So I can take any number and mod it by 2 and get the 0 or the 1 out of it. So if you notice right here, the 2 modded by 2 will give me a 0, and the 3 modded by 2 will give me the 1. And the -1 modded by 2, I don't know if it will give me a 1, but it just depends how JavaScript works. When it comes to modding negative numbers, the language plays a big role. Different languages might have different implementations of how to do it, but a quick way to do it is pull the console of your browser, go to, where is it? Oh, I am in the console, and just do -1 modded by 2. What does that give you? It gives you -1. So the modding does not really work right here because I want 1, I don't want -1. So maybe I can hard code this case. And for these two cases, the carry is the same, right? And the result of the addition that I'm going to add to the answer is just modding the result whenever the result is bigger than 1. So I can combine those two cases to one case that just says if the result is bigger than 1, just take the result and mod it by 2, and that should be fine. If I run it, it'll work just fine. Then for -1, I can say if the result is less than 0, I'm going to run this logic. That means it's -1. And if it's not 0 or not 1, if it's not any of these cases, that means the result is 0 or 1. In this case, I can just add it to the result, and my carry is equal to 0. Now, so this cleaned up the logic just a tiny bit. Now we can look at this handling the carry logic. So it's adding 2 elements or 1 element to the beginning of the array. It's very simple. I don't know if it could be simplified more than that. It's just 2 cases that I need to detect, and it's either I'll add a 1 or I'll add 2 ones to these cases. Now let's think about removing leading zeros. So let's say you add 2 really big numbers, -1,000 and +1,000. So if you remember the notes that we did in the beginning of the video, we'll get a big list of zeros. So imagine this while loop running through each one of these zeros and removing it. Maybe a better idea here could be, hey, I'm going to have the while loop calculate how many zeros I see that are leading zeros, and I'm just going to chop them off one time in one take after running the while loop. So that might be a better logic than just removing the elements one at a time. So here I'm going to say number of zeros is 0 to begin with. and I probably need a counter so I can increase it with each while loop. So I'm going to use, instead of I, I'm just going to use a temp. I'm going to call it 0, and I'm going to start from the beginning of the array all the way to the end. I'm going to ask with array at temp if it's equal to 0, and of course I'm going to check the zeros all the way to the last 0. I don't want to check the last 0 because if the whole answer is a 0, I need to leave the last 0. I can't remove it. So that's why I can't have my temp to be I can't have the temp being or hitting the last index. It should be less than the last index. It can't be the last index because the last index will be the 0 that I want to leave in the case that the answer is 0. So I'm going to loop through all of them from the beginning, and temp should be at max less than the max index. And the max index for array 1 is just the length minus 1. That's the max index I can reach, and I should not touch it. So it should be just less. And through each iteration of this while loop, I am going to increase the number of zeros. Now I'm going to increase my counter. The reason I can check or I can safely increase the number of zeros is because I already did the checking right here. If the element that I'm looking at this index is a 0, and my index is safe, it's maintained by this condition, that means this is a leading 0. I'm going to count it, and I'm going to look at the next in the array. So now, since I have the number of leading zeros, what will this enable me to do is running a method called slice. And this method is going to chop the array. And I can tell the method to chop the array from a specific index and give me the last. So chop the beginning, throw it away, and that's where my leading zeros are at. The leading zeros are in the beginning. So I'm going to chop the beginning of the array using the slice method. For more information about the slice method, you can just check it on the MDN JavaScript documentation. So I need to chop at an index I need the chopping to start at an index where no leading zeros where no leading zeros exist. So the way I can do that, let's do a quick note here. So let's say my array is 0, 0, 1, 0, 1, 1, 0, 1. Okay, I need to get rid of these zeros. Those are the leading zeros that I don't want in my answer. So, and in this specific example, my num of zeros will be equal to 3, because there's 3. And I need the chopping to happen right here. What is the index of this element? The index of this element is 3. And my number of zeros is 3. So this is a 3. So I want to chop at index 3. And this index is just indicated by the number of zeros that I have. So I can just use the number of zeros with the slice method to chop the beginning of the array and get rid. You can think of it as getting rid of the first 3 elements of the array if you use the number of zeros. All right, let's see if this works. Let's try to submit it. So see, I don't trust these numbers. All right, so in this case, we got rid of the multiple unshifts with the array, and we just ended up chopping the portion that we don't want. We simplified some of the result logic, and this logic right here is a little easier. We only needed to know this, which one is the smaller array so we can pad it. And this way, the logic is simplified and space is optimized and complexity is optimized. It's still big O of n, or it will be big theta of n, because I'm going to have to run through all of them most of the time. Or all the time, not most of the time. All the time I'm going to go through each element of the input arrays, but I'm not using any extra variables that depends on the input to record my answer. I'm just using the input arrays to do the answer, so I'm just using constant space. The space that I'm using for the solution is not growing, and that should optimize the solution to the maximum of my knowledge. That's what I would do within an interview. I'll try to do it a little faster, but I'm still practicing, and that should do it for this video. Again, I'm gonna hopefully be doing some more videos. I'll just make my face a little bigger again. So I'm gonna make a little more of these videos. I'm doing interview prep, so I thought I'll just record my interview prep. It will be helpful for everybody. It looks like the format that I want to do is that I'm going to go through a big video of walking through and learning the problem and researching the principles behind the problem. Then I'm going to do a second shorter video that goes through a quick answer to the problem and optimizing the solution to the best of my ability. That should wrap it up for this video. If you want more details about this problem, you can check out my previous video. I'll have it in the description, and see you guys later.